First, I would like to introduce our journey. My name is Fu Zui, come from National Taiwan Normal University. Here is Professor Yao, come from Dongdeng University. Professor Li, come from National Taiwan Normal University. Professor Jiang, come from Haiyang University. Professor Xu, come from National Union University. Now, please introduce your team. For report first.
Hello everyone, I'm Chen Tinghao from New Zealand Capital, and this is Hong Li from, and this is Tanzania, and this insurance, and this you're from Jason. Okay, thank you everyone.
The opponent.
Hello everyone, this is Team TYPT and I, Hong Yubo. He's Chen Yeojun, he's Yu Dayou, he's Qiu Songren, and he's Hong Yufang.
We are Team South here, and we are from Concordia Middle School. And I am Chen Shaochen. This is Qiu Jianjun. This is Liu Xingyu. This is He Ziwei. This is Li Yun.
Thank you. Now, please, we start and the first challenge. Please.
We would like to challenge question number 4, climbing magnets.
Accept. 4. Please write presentation name on the blackboard. Report, please.
Well, hi, I'm John. I'm from the team Museum, and today I'm going to introduce a phenomenon that calls timing mechanism. And the first, let's see the things that I'm going to talk later. So the first is the problem statements, and the second one is the experiment setup. And if you have experiment, we do the experiment, and we got a result. And we got a result, we can use the theory to explain the result we got. And last, we can get a conclusion of the theory and the experiment data. And the first, let's see the problem statements. And the main point is we're gonna explain this phenomenon and illustrate how the rest of having depends on the length parameters. And there are some focus points of the problem statements. And the first, and we're gonna use the theory of this phenomenon to discuss about the phenomenon. And the second one, we do two parameters to which affects the rate of climbing. So we can get the data of experience, and then we mix the theory and the data of experience, and then we can get a result and a conclusion of this phenomenon. And the first, let's see the experience setup. And here is and the first one is optical detector, which used to control the rotating speed of the motor. And there are one magnetic rod on the motor, and we use the screw to make sure the magnetic rod won't shaking. And we got a magnet and the clay. The clay is used to increase the magnetic mass, and the clay won't affect the magnetic attraction. So the magnetic force won't be affected. And the next is the experiment. So the first parameters, there are two parameters. And the first one is the mass of the magnet, and the second one is the rotating speed of the magnetic rod. And there, the first parameter is the mass of the magnet, and we got a number of magnets. No, it's the mass of the magnets. So the first one is 60 grams. We use 6 magnets and its mass is 6 grams. And the second one, we set the mass as 39 grams, but we add 3 grams clay to increase the mass. And the last one, we add the 5 grams clay to increase the mass. So we set the rotating speed as 2.5 grams per second. So yes, and it's the same as these three experiments. So let's see the result. And here is the video of the timing magnets. And here, and this is the 36 grams, and the second one is the 39 grams, and the last one is the 41 grams. So let's see the graphic of it. And the first graphic is the 36 grams, and we set the Y is the timing rate, and the X is the time. And we can get a highest. We use tracker to check this magnet mass, like the point is here, and so we can get this graphic. So we can get a highest timing rate, which is 7.121 centimeters per second, and we can get the average timing rate, which is 1.07 centimeters per second. And we smooth the data to reduce the natural noise or other affection that is not in this experiment. So we can get this graphic. So we can see the highest timing rate at 25 seconds. Here is the peak of in this graphic. So here is the 60 grams, and the next one is the 39 grams. So as you can see, the highest timing rate is 5.808 centimeters per second, and it's less than 39 grams and 36 grams. But the average timing rate is 1.21 centimeters per second. It's higher than the 36 grams. So let's see the smooth data. And here you can see it has the highest peak as here in this time. So here is the last graphic of the experience. So here's the 41 grams. So you get the highest having rate, which is 6.632 centimeters per second, and its average having rate is 1.268 centimeters per second. So we also smooth the data, so we can get this graphic. So we can get a highest rate here. So for this experience, we can get the mass can affect the speed of climbing. So we get the mass, which if the max increase, it decrease, so the climbing speed will increase. So and then here is the next parameters. We do the next parameter, which is the rotating speed of the magnetic rod. So we control the motor's rotating speed to do this experience. So we set the rotating speed is 2.5 rounds per second and 5 rounds per second, and we set the number of the magnets as n magnets. Okay, so and the mass of this is 48 grams. And here is the result. And here is the video of it. And here is the graphic of 2.5 rounds per second. So we can see the highest climbing rate is 8.108 centimeters per second, and the average climbing rate is 1.727 centimeters per second, and it's here. And we also smooth the data, so we can get another graphic of it, and we can also get a highest climbing speed. So the next is a 5 rounds per second. So here we can see the highest climbing rate is 8.108 centimeters per second, and the average rate is 1.727 centimeters per second. So you get the highest rate here. It's 6.5 seconds to between 6.5 seconds and 77.5 seconds. So yes, we smooth the graphic, so we also get the highest rate. And now here is we think the rotating speed can affect the speed of climbing. So we think if the omega increase, the climbing speed will increase too. So let's see the theory of this phenomena. So the first one, if you got the magnets and the magnetic rods, we have the magnetic attraction, which will cause the normal force of it. And if we have the normal force, we can get a friction force. We can get a friction force between the magnetic rod and the magnetic surface. So here. And the next is the friction force. There are two friction forces in this phenomenon. The one is tangential components, and the second one is the vertical component. And the directions of these two friction forces is different. Yes, and here is the tangential. Here is the tangential frictions of this phenomenon. And here, this friction is mainly responsible for the rotation, so we can get a formula like this. And this mu is the friction value of between the magnet and the magnetic rod. So in this theory, we can get a so we have the friction, right? And so the magnet will move with the rod surface because of the frictions. And the last we can get stick shift phenomenon. So what is stick shift? Here you can see the cabin looks like it's shaking. It's shaking, and the stick is like it moves this way, and the rod is rotating like this, and you move it. But there's a blocker to let it go back, and here is the stick phenomenon. So we can see the graphic of this. We can see the x position isn't stable. So here, so we can get a stick shift graphic of it, and the next we also smooth it out. So we can see it's also an unstable value, and this, and we can get this phenomenon. So we use Newton's second laws to explain stick shift phenomenon. So it's stick force and stick last. And here is the vertical motion, which responds for climbing. So here is the vertical motion, and the final of it is a net vertical force component. So we can get this phenomenon, and we can get this. And we can get the chemistry is many effects about the rotating speed and these two values. And here is the rotating speed effect. So if the rotating speed is too low, and you won't go up. So here is the graphic. And now it's the conclusion. So if the omega increase, the time speed increase. So and the experiment shows if the mass decrease, time speed decrease. So thank you. It's all my report.
Question of opponent.
Okay. I would like to ask that you mentioned a lot of time in your presentation about smoothing the graph. What do you mean by that?
It's because there are some that to let the value they are unstable. So we can use this to get a this line to explain the theory well.
Okay, and can you turn to page 18?
Thank you.
Yeah, one is the time at 13 and 14 is incontinuous.
So because the y is too small, because there are more. The graph is too small.
Which you consider two factors, right?
Yes.
Which one you think is the major factor that would impact the velocity factors?
So is a timing velocity?
Yeah. Which affects more? In your opinion?
Affect more. So here is vertical motion.
No, I mean like you consider mass and the rotating speed of the rod, right?
Yes.
These two factors which will impact the velocity of the vector that goes up the most.
I think both. But the rotating speed is the mainly. I think the rotating speed is the mainly key of the.
Any evidence in your presentations?
No.
Oh, okay. And you used, I saw you calculate the static friction. Like why is static friction? Can you explain? I didn't understand. About page 33.
Center?
Back. Yeah. 34. Yeah, why is static friction?
It's the
Time is up.
Honorable judges and University reporters, I'm from Team TYPT and I'm going to oppose program members for clamping magnets. And this is a problem statement, and reporters are focusing on how the rate of clamping depends on relevant parameters like they mentioned in the presentation mass and the rotating frequency of the rope. So the summary of the report is that the magnet clamps up the screwdriver as it rotates, but it doesn't mention what rotates. Like in our opinion, that it is actually two things rotating. And in the theory, they mention a magnetic force slip phenomenon, and they also consider friction. And in their experiment setup, they use a screw and a clay to add mass to the magnets. And the parameters they use is mass of the magnets and the rotating speed of the rod. And also they think that they change the rotating speed like 2.5 and 5 rounds per second with 8 magnets. So there are some pros and cons about the reporter's reporting. For the pros part, they provide a rigorous experiment considering a wide range of parameters and a subtle series deviation. And for the con part, they lack some notations about the singles used in the series, and they also lack the explanation of slip things. And they didn't elaborate on why they choose to consider a static friction instead of kinetic friction. So here's the discussion part. For the series part, I'm curious about why the boundary conditions is not clearly defined in your presentation. And about in the page 46, how do they derive the formula? And as for the phenomenon parts, I'm curious about why only quantitative results in their presentation. And also in the page 13 to 16, why is the speed increasing? And for the tracker class, if you use tracker, why is that your data point oscillates that much? And why you can just smoothen it? And for the other part, I only see 5 data points in your presentation, and I think that is insufficient. And how are those data smoothened? You didn't mention how you do that. You just said you do average, then y average. And in page 43, you say that there is an uneven distribution about what, and how unevenly they distributed, like 3 to 4 or 1. So I would now like to invite a reporter to discuss with me. So for the other part first, I would like to know why you only conduct 5 experiments and you can have a complete.
Because I didn't think that through, so I didn't get a perfect number of the experiments.
You didn't, I mean, you only consider 5, you only did 5 experiments, right?
Yes.
So did you think that is sufficient to support that your theory is correct?
No, I think I can do more experiments and add some similar like console.
Of simulation?
Yes,
Oh.
simulation.
Okay, and about page 46, how do you derive your equation? That is the most important part of your report.
Is that page 43?
46.
46. Okay, here.
Yeah.
I searched for these two.
Oh, you use it from you get it from the paper.
Yes, yes.
Then is there any conditions that need to fit? If you want to use this equation, is there any conditions need to be fulfilled in your paper? Have you read that already?
Yes, but I didn't read so we get an A and B, right? And so
No, I mean this is correct if you get it from the paper.
Yes.
But I mean, if I think that there is some conditions that you need to be fulfilled in order to use this equation in your presentation, in your experiment.
no,
So
I didn't.
there is no conditions.
So I didn't do this.
You did not know the conditions.
Yes.
Oh, okay. About page 13 to 16.
13 to 16.
Yes. Yeah. Next page. Thank you.
Like this
Why is this increasing? Like I can see that there is the trend that is going up and up. So can I say, did you think that when the time goes forward, it will also goes up and down, up and down again?
Yes,
Or it will
because there are friction between yes, press. So the surface between it will change. It will change it. So
So you think it will continue to increase?
no. Yes. Yes.
No any boundary conditions?
I think it
increase to
will
infinity.
it will still look like this.
Uh-huh. So what's the maximum? Like you calculate with your presentation.
No. And then
Okay. Then can you say that why did you consider a static friction instead of a kinetic friction?
you say in the theory.
Yes. Like did you think that it is rotating while it's static?
Just the surface, right? The surface. So
Can you draw it on the blackboard, please? Thank you.
here is the mechanical block, right?
Yes.
And the mechanism is here. So it is rotating like this, and it will look like this, right? Because of the friction. Because of friction, it will rotating like this.
So why is that?
What's that?
Like, actually, in my opinion, I think that as this rotating, this also rotates in this direction, but it will also rotate in this direction, right? So it's actually 3 things that's rotating, but you only consider like the rod's rotating and the magnet is not rotating, right? In your experiment.
I didn't consider that. That's very low. I will
Oh.
consider one.
You didn't consider that?
Yes.
But I think that in your presentation, your focus is on how this rotate goes up will be affected by the omega of the loss or the mass of this. So it is not this will rotate around the rod goes up and this rotating.
Yes.
So the contact between the rod and the magnet is a line, right? It's not a surface. Do you agree that?
Yes.
So, and as you're rotating, the contact line changes. Do you agree that? So here will be the pivot point. Okay? So this actually rotates in this direction. So why did you consider a static friction instead of a kinetic friction?
I
Okay. About the tracker plot you provided in your presentation, anyone is okay. Because I see that the error is quite big. Can you explain how this oscillation is get, where this is get? Like, why will the oscillation? If you
Is it mixed or big?
yes.
Oh, because just as I said, surface is different. The surface is when the experience going, the surface will changing, so the friction between it will be different. So sometimes it won't the velocity will decrease, but because
Then why did you say you smoothness this data by calculating its average? Because I think that this is extremely large errors here. So why you just calculated the smoothness plot in your experience, in your data? Yeah. Why?
because we can get average velocity this large. So
Yeah, I mean that.
so the peak of it won't completely.
Yeah, but it is oscillating. So can you go back to the video? Yeah. Like I can see that the trend here is actually so that not that obvious, but I think it's going up and down and up and down. Why? But in your next page, it's continuing going up.
So maybe I do the wrong. I smooth I go use the wrong way to smooth.
So, okay. In my opinion, I think it is not you use a wrong way. I think you use a wrong analyst to do this experiment. You cannot just calculate its like average. You add it up like this too. Like if you calculate its average, it is highly sensitive to their extreme value.
Oh yes.
Okay.
I know.
Okay, and in page 19, please. Thank you. Yeah, you here provide a qualitative conclusion. Can you give me a quantitative one?
Say
19. Yeah, you say n decreases and the climbing speed will increase. Like exactly, what's the exact value or the formula you have? Yeah, I would like to know the quantitative results.
I'm sorry, I didn't put a formula on this.
You didn't put a formula.
Yes, I didn't do it, but
So in your page 46. So mass is not considered in this equation, right?
yes.
So,
But I think the NMV can be calculated if we add a gravity, smaller gravity.
so what's the condition that we can use this equation? Because I asked you before, and you now say you didn't consider gravity. Okay, never mind. And what's A and B will be? What one thing I changed? Like you say, A is a scaling factor, like represents the proportional relationship.
Yes.
Like who will determine A in different equation?
I think it's the friction.
Friction?
Yes.
Okay. Then as for damping factor, you said that controls the rate at which speed decreases at high omega. Like the control the rate, which rate? The rod rate or the magnet rate?
Well, the rod, magnetic rod, rotating rate.
This or this?
This. So,
This one's rotating rate.
yes.
So you think that the damping here that affects this rod will have a high impact on how this magnet climbs up.
It's because if it's too high, it won't climb it up, but it's too low, it won't climb down too. So we can get up.
Can you rephrase it? Like too low, it will.
You won't climb it up. If it's too low, you won't climb it up.
And did you say that in your presentation?
No.
And what's the exact? Like you say too low, but exact how low?
I didn't do experiment on it.
So you think that? Oh, okay. Then you just know that.
Yes,
You know that you need to be at least like 5 centimeters high to let it go up. Like you need to have a boundary conditions that you have already have a here. Like you say it's too low, or you mean like the angular velocity here is too high.
can see in my experiments.
But you only provide 2. How can I know the trend? Like I only have 2 data points.
Can you please say it?
You only provide 2 data points, and in continuous data point, like how can I make sure that the trend you are going to say is correct? Since I don't only have 2 data points.
So that's because I didn't do so more experiments.
So I think if you have more time, it is more convincing for you to do a lot of data points. So instead of just considering 2 parameters, I think you can rather focusing on 1 and do it to the better.
Okay.
Like provide both qualitative and quantitative results, and provide a more data points, like, and also calculates the error between your theoretical model that you use in your
Okay,
case.
so I can do more experiments, right? I can fix it with the similarity by console or Python or Python.
Okay. And also, can you page? Oh, that's all. Thank you.
Reviewer, please. Review, please.
So here is the summary of report that and also concludes that what I have discussed with the reporters. So as for the discussion part, we consider the conditions of reference about formula on page 46, and also why there is only insufficient data provided. Also, why only considered static friction. Like we discussed in the blackboard, like there are actually 3 things that are rotating. So I don't know what the reporters means, like the static, who and who is static. And also, they didn't say that the oscillation and tracker plot, they didn't give a convincing reason why this occurs. And also, I asked about the smoothness result. Why can he do that? And he also didn't provide a persuasive answer. He only said, and it does not correspond to the tracker data points it provided. So it's, and also the A and B on the formula 46 is.
Reviewer, please.
Okay. Questions to the reporter. Could you please tell us what are all the forces that make the magnets climb up?
Oh, the friction.
Could you just give me like a general answer? Like all the forces.
Vertical components. In this formula.
So basically, you're saying only friction causes the magnets to climb up.
Yes.
Does the opponent agree?
I disagree. I think that torque also affects it.
So what are the forces that causes the torque to happen?
Okay, can I use the? I think that, as I mentioned with as I discussed with the reporter,
No, excuse me. Just give me a short answer.
like what the gravity here will make the force.
Okay, so gravity.
Yeah.
Okay, thank you. Next question. If we change the sizes of the magnets, what do you think will happen to the experiments?
Sizes?
Yes, the sizes of the magnets. So for
You
example,
mean like mass or?
no, I mean like the diameter of the magnets.
So you maintain the mass and
Yes.
use different.
Yes.
So you change the density.
The diameter of the magnet.
Okay. So me or?
To the opponent first.
Okay, I think it will, because the gravitational force is the same. So I think the torque part will not be influenced that much. But I'm not quite sure what will affect by the friction one. But in my opinion, it is not that much.
Can the opponent, can the reporter present?
Yeah, I think the torque of it will be affected just because you increase the diameters, the speed of it will be decreased. So I think the torque will be decreased.
The opponent mentioned that there are some that the reporter didn't mention any critical conditions in his experiments. So could the opponent maybe predict the critical conditions of this problem?
Yeah, I mentioned a lot of boundary conditions in here.
Could you predict them?
Like which be more specific
For example, for the mass.
for the mass.
Yes.
So like what mass? Like the minimum mass
For how large of a mass can the magnets not climb up?
how large?
Yes.
I think that has something to do with the magnetic force between them. So I don't think that is only considered, that only be affected by the mass.
Thank you. So randomness slip vertically, you think that the magnets will climb up just only because of friction to both of you?
No, I also mentioned.
Just clarification, you mentioned for torque and friction, and for clarification, you mentioned only friction. And that'll be all for our questions. Honorable juries and fellow competitors, I am the reviewer from Team Excel here. For today, I'll be reviewing problem number 4, climbing magnets. The problem statement reads, attach a rod assembled from cylindrical neodymium magnets horizontally to a vertical ferromagnetic rod. Limit the motion of the magnets to the vertical direction. When the ferromagnetic rod is spun around its axis of symmetry, the magnetic rod begins to climb up. Explain this phenomenon and investigate how the rate of climbing depends on relevant parameters. For today, we'll be mainly focusing on 2 points. First, why will the magnets climb up? And second, how will different parameters affect the rate of climbing, meaning the speed of climbing? Here is a review of the report. For the phenomenon, he basically just described how the magnets climb up. And for a theory, he mentioned about the Stickson phenomenon and Coulomb's friction. And for experiments, he conducted 2 parameters. First one is the rotating speed of the rod, and the second one is the mass of the magnet. For the mass of the magnet, he attached some clay to the magnets to ensure that the magnetic strength wouldn't increase. And for his pros and cons, first he provided a demonstrative phenomenon for the problem. However, he had a lack of parameters and he didn't have a complete and whole theory. And he also had a clear observation video that shows the magnets climbing up. However, the reviewer would also like to clarify that the magnets are also spinning, and it would be better if the reporter showed that the spinning of the magnets in an observation video clear as well. However, he had a lack of qualitative and quantitative explanations, and also he had a lack of error bar and theory line to make his experience not so to not ensure his experiment's validity and accuracy. And also, he explained the causes of the phenomenon, which is friction in his point of view. But, however, he failed to explain the physics behind the parameters, and he had a clear explanation of his theory. However, he had a lack of explanation of critical conditions. And for the review of opposition, he noticed the lack of explanation for the theory. However, he didn't notice about the lack of the theory line and the error bars. And he noticed the lack of the experiment. And however, he didn't lack a discussion of the entire theory itself. And also, he discussed about the accuracy and analysis and experiments. However, he didn't discuss about some clear deviations, such as the rod is actually shaking. And he asked about the boundary conditions. However, he failed to notice the lack of parameters. But he also did notice about the lack of quantitative explanations. And on their first key discussion, the validity of experiment, the opponent asked, why did you only conduct 5 experiments for parameters? And the reporter thinks we have data enough and we have simulation to support it. However, the review agrees with the opponent that to ensure the validity and accuracy for experiments, we believe conducting more experiments and adding a theory line and error bars are actually necessary to make it easy to believe. And second, the reason of using static friction, and the opponent asked, why did you use static friction for your theory? And the reporter said, the reporter replied with drawing the graph, but however, he agreed with the opponent in the end. And the reviewer believes that both static friction and kinetic friction was included in the process. And for our question, what are all the forces that allow the magnet to climb up? The opponent thinks that torque and friction will also affect the climbing motion. And the reporter thinks that only friction. And the reviewer agrees with the opponent. For the points missed, they didn't discuss about the magnetic strength for the parameters. And for the discussion, the reviewer believes that the discussion for the theory is oversimplified and there could be more. And for experimental deviation, they then discuss about the uniformity of the plane, meaning how the mass is attached, and also the shaking of the rod, which is contradictory to the problem statement. And that is the end of our review. Thank you.
Hi, I'm the reporter from Team Music, and here I got a conclusion of my report. And since the problem that Apple asked me and the reviewers point. And the first line, I didn't explain how I smooth the data. I just used Python, but I didn't explain. And I can only use the average value to smooth the data, so it will have some error of the graphic. So, and the second one, I didn't explain what is the static friction. So, and the third one, I think the manifold is the friction force, but there are another force which is gravity to affect the climbing speed. And the next one, I can do more experiments to prove my theory is good and my formula is right. So, and I also can use console or Python to make sure my value is right and to find out which rotating speed or which mass can have the highest climbing rate of the magnet. So here is all my conclusions. Thank you.
First, use face recognition to unlock
Board
the
3,
device.
any question or comment?
I have 2 related questions. The first question is, if you reverse the rotating direction of the ferro rod, do you expect that the magnet is still climbing up? The first question.
Yeah, I think it will still climb up.
Yes, however, we believe that when the magnets climb up, it would spin in one direction. So when you spin it like this, it would spin. But if you spin in the other direction, then the magnets would spin the other direction. But also climb up.
I think too, because if you change the rotating way of the magnetic rod, and the magnets will still coming up, but there are some difference. The magnet's rotating direction is different.
Okay, the follow-up question is, if you expect that the magnet is still climbing up, there must be some sort of physical parameter to break the symmetry because the gravity direction is still the same. So could you explain what break the symmetry? If you reverse the direction of the rotations, then that means some sort of force or torque is reversed, but your expected motion is still climbing up. That means something is breaking the symmetry, right? Then what is that thing? Oh, okay.
We believe that overall, first, we actually believe that there are two different types of torque for this problem. There is the counterwise torque and the counterclock torque. And when changing the spinning of the ferromagnetic rod that the jury mentioned, you would just change for example, originally it was like the counterclockwise torque that was bigger. Then if you change the spinning, it would just turn the clockwise torque bigger. However, it would still climb up.
Okay, then how about the answer for not the answer? What do you think?
90% agrees with the reviewer, but a little bit difference is that he mentions that the only changes in is the direction of the torque. But I think the friction also changes. So I think it's those two factors that both will affect this, not only just the torque mentioned by you.
I think if you change the direction of the rotation, it won't affect too much because the surface between the magnet and the magnetic rod is the same. So the friction force is the same. And the torque, because you use the same magnet and the same length of the magnet, so the torque is the same. I think the torque is the same and the friction will be the same because of the surface.
Marking time. Reporter. Six, 4, 4, 5, 5. For opponent. 8, 7, 7, 7, 6. For reviewer. 9, 8, 7, 8, 7. Thank you all. Rest to 9:35. 然后同学们就拜托换位置，然后检查设备。